So next up, we have Karin. She's nearing her completion in her industry PhD at Deakin University in collaboration also with the ARC Training Centre for Green Chemistry and Manufacturing. With a strong foundation as a research and development chemist in Brazil, she specialises in the synthesis of solid lipid nanoparticles via double emulsion using the drug DETC, work that led her to publish the article, bear with me on this pronunciation, diethyl dithiocarbamate loaded in beeswax cobaba oil nanoparticles obtained by solventless double emulsion technique promoting death in vitro. Karin's contributions to the field have earned her a graduate research training fellowship in Deakin's School of Life and Environmental Sciences. She continues to advance innovative, sustainable approaches to chemistry, most recently presenting her research, radial flow stream splitting for improved separation and workflow to a greener approach to astaxanthin analysis at the IUPAC 2025. So well done. We're very lucky to be able to hear this presentation from her tonight. So over to you, Karin.
Thank you so much, Adele. Now, bear with me. I am going to share my screen, and I can be a little bit slow with that sometimes. Don't ask me why. Where is my sharing? Where is my sharing? Oh, there you go. All right. Can everyone see this?
Yeah, all good.
Yeah. So today I'm going to be talking about a very important part of my PhD. But before I get into that, I decided to give a personal touch to this presentation and talk a little bit of my journey as a chemist. So then everyone will understand why a Brazilian ended in Australia, but also is a message to never give up. We will get there. So essentially, I studied industrial chemistry as an undergrad, and I was very lucky that I had the opportunity of working in a research lab during my undergrad, where I did a little bit of organic synthesis and characterization of compounds. And then in the very final year of my undergrad was required to do internship in industry or in a commercial lab. So I got this part-time job where I was doing very basic analysis of water and effluent, but it was pretty good because I started to build a little bit more my knowledge in analytical chemistry. And then in 2015, I started to do my master's degree in chemical engineering. And as Adele mentioned, the main focus of my master's was the development of lipid nanoparticles, which led to a publication, which I will always say that is my baby because was always and will always be my first publication. So when I finished my master's in 2017, I got into a point where I was either underqualified for more senior jobs or overqualified for other more, key kind of jobs. And it started to get very, very frustrating. And also Brazil was in a massive crisis as well. So basically, I couldn't get any job. I had a few contracts in the meanwhile, but it was never something really solid. So got into a point I was like, yeah, never mind. I gonna try something else. So I always had in my mind that I want to travel abroad. I want to improve my English. And I said, yep, I want to live in Australia. That's where I'm going. And I actually ended living in Ireland. So funny story, essentially, because in Brazil we still use travel agents, trust me, for helping you when you want to go abroad. And I got there and I said, well, I want to go to Australia. I want to learn English. I want to work part-time. And they said, well, it's not going to be that simple. One, you can't work part-time, and the others, you need to have, I can't remember, it was a ridiculous amount of money in my account. And then the lady said, why not Ireland? And I was like, well, why not? So I moved to Dublin in 2019, and I was meant to stay there for 8 months, only learning English, working a little bit. And then after that, when I had my English good enough, if I can say like this, I was going to start to apply for a job. And then we all know that COVID happened. And when COVID happened, we were all stuck at home. I was stuck with other kids because back then I was working as an au pair, which was quite frustrating because I knew my potential and I knew what I want to do. It was just not possible. But I didn't give up. I started to apply for both jobs and PhDs, and I knew that I want to go to Australia. So I still remember that I put it in a board. Where am I going? Australia. Doing what? PhD. There you go. And then in 2020, I finally got this amazing offer. Tony, you may not remember, but I still remember our first interview, which is for the PhD that I'm doing today. But there was only one problem, which was COVID. And I sure remember, like, it's very vivid in my mind that I would email my current supervisors saying, please hold my scholarship because eventually I will be able to go to Australia. Because back then I was just like stuck in Ireland. I couldn't even go back to Brazil or, get a visa to Australia. So what I could do during this time, travel around Ireland, and I had a little bit more of life experience. And then in the end of 2021, the borders in Australia were finally opened, and then I managed to start my PhD, which I was very lucky to be under, the wings of Tony, and I had the chance of, meeting all these amazing PhD candidates in the center. So just for you to understand, my PhD project was designed in partnership with Ridley Aquafeeds, which is one of the largest animal feeds in Australia. And the opportunity was a lifetime opportunity, basically. So I not only had the chance of making the connection with the industry, but also I had the chance of doing an internship there, where I not only learned the methods for analytical methods in general, but also I got to understand and learn about the business, how the business is run, and everything else. So it was a very, very nice opportunity. And just an overview, what was meant to be my project. So don't worry too much about the names right now because I will explain a little bit better in the following slides. But when I came to Australia, the main part of my PhD was to get the synthetic form of astaxanthin, which is a carotenoid used in aquaculture industry, which I will explain, and microencapsulate this carotenoid, or in better words, stabilize it, and then include in aqua feeds. So I did all these steps. I developed the methods with my previous supervisors. We had amazing microcaps. And then when we get into the extrusion trials, which is a step where we want to test the microcaps into the feeds, it didn't quite work as we were expecting. And then obviously the clock for my PhD was keep it ticking. And I knew that Ridley also wanted to test these feed with the microcaps to feed animals as well, which was a completely separated project from mine, even though it was a little bit connected to each other. So we needed to move a little bit, and that's what brings me to what I'm going to be talking today. So not only was to microencapsulate astaxanthin, but also I needed to develop a robust analytical method where I could quantify and qualify astaxanthin in finished products. Which brings me to talk to you a little bit about radial flow stream splitting. But before I get into that, I need to just have a quickly step back and have a chat with you about chromatography columns, because that will help you to understand where are the challenges and which problems I'm trying to solve with this new technology. So essentially, during the packing of a chromatography column, the particles are pressed with high pressure, and this pressure is applied along the length of the column. and it will result in variation packing density in both axial and radial directions of the column. And this variation in packing density, especially in a radial direction, will result in distortion of the solute plug, which will greatly decrease the separation performance of the column. Additionally, due to this variation in packing density in a radial direction of the column, we have what is very well known in literature as the wall effect or radial heterogeneity. And what happens is the radial central packing density of the column is actually much lower than the wall. So as a consequence, our mobile phase while we are pumping, what will happen is the bands will be migrating much faster in radial central section of the column and much slower near the wall. And then we will have a bowl-like parabolic movement of the solute plug. So as a consequence, more plates will be required to separate the bowls than thin rectangular plugs. And consequently, to separate these bowls usually is required long columns. Long columns consequently requires long methods. Long methods involves usually high pressure. And then depending on how high the pressure is, we need to slow down the flow rate again. And what we will have is peak overlap, pore separation, or what I say is a nightmare for works with chromatography is regular or broad big shape. So how can we mitigate this problem? That's where radial flow stream splitting, or as I'm going to be referring to, RFS steps in. So when we are redesign a chromatography column to enable the RFS to be working, we need to have a few key concepts in mind. So essentially the wide bore outlet of the column has an outlet fitting that has an internal bore similar to the column in diameter. This wide bore outlet will have a variety of inserts for flow control, and these inserts will be seated into this wide bore outlet of the column, allowing it to be operating in a variety of ways. What I'm going to say is regular or radial flow splitters, which is the main topic for today. So for you to understand what is going to be happening with our mobile phase when we are enabling the RFS technology. So essentially the sample will be carried through the column, and it will exit from the column bed, and it will be channeled through two outlet flow paths, one peripheral and one central. The sample is carried through the central section of the column, essentially free from the wall effect. Important to mention is these two flow paths will be remaining separated all the time, and that's where comes one of the main advantages. Only the radial central flow will be actually sent to the detector. So you can actually even be working with two detectors in parallel, because we have the peripheral and the central flow of the column. And because of that, less plates will be required to separate the leading surface of the bowls as well. Also, another very good advantage is these columns usually operate with only 30% of the central flow path being sent to the detector and the other 70% being sent to waste, for example. And this comes very relevant when you are working with equipment such as mass spec, where your flow rate needs to be very well controlled and needs to be slow. Because only a little portion is sent to the detector, it means that you can increase your flow rate of your method without burning your detector. So we applied this technology for astaxanthin, which was the main focus for my project since the beginning. So just for you to understand what it is astaxanthin. So astaxanthin is a xanthophyll carotenoid, a lipid-soluble pigment found in marine animals, plants, and fungi. The chemical structure of astaxanthin is quite complex, as most of the carotenoids. It is formed by conjugated double bonds, but also it does have these hydroxyl groups attached to the ends of the molecule, over here and over here. And what happens is The combination of the conjugated double bonds and these hydroxyl groups gives astaxanthin this very powerful antioxidant activity. So that's why nowadays we can go, for example, to the drugstores and find astaxanthin being sold, as an anti-age kind of ingredient. But important to mention is neither animals or humans can synthesize astaxanthin de novo. So if you want to have the benefits of astaxanthin, you must be included it into your diet. Astaxanthin received a lot of attention in the past few years, especially in Australia, because of its use in aquaculture industry. So in aquaculture industry, not only the nutritional benefits of astaxanthin is relevant for them, but also the fact that first, I don't know if you know that salmon is actually not naturally pink. The red-orange coloration present in salmon's flesh is due to the presence of astaxanthin. So, because farmed salmon cannot acquire astaxanthin from their diet as wild fish do, astaxanthin has been used or added into feeds for a very, very long time. And what happens is astaxanthin is not only a very expensive ingredient, but from an industry perspective, it requires a lot of complex analytical methods to accurately quantify or qualify its presence in the finished product. And why is not going ahead? I don't know what I did.
You've got your pointer on, Karin.
How do I remove
There
that?
you go. You have to right click, but go put your mouse across, and then click that one. That one should work. There you go.
Yeah, I'm gonna do this. Sorry, everyone. Which brings to the aims of my project. So I want to access if RFS or radial flow stream splitting and conventional chromatography when analyzing products containing astaxanthin. So can we modify the extraction methods being currently used in the industry for a greener option or something that would less solvents? And will the chromatography separation be improved when we use this new technology? And importantly, will this technique be greener? Just to give you a little bit of a perspective of how the analysis of astaxanthin has been conducted in the past few years, usually the extraction methods involves long process. So here I'm just showing what was done when it was with fish feeds. So it involves 2 hours digestion and then a very long time for solvent extraction using very toxic solvents such as chloroform. And then when we go to the step of the analysis of the separation analysis is also a very long method that also use a combination of several solvents such as ethyl acetate with methanol and water. So there were two aspects here that I want to change. One was the solvent extraction, and the second part was the separation methods that are out there. So very quickly here, me and my supervisor decided, okay, most of the time the industry only needs to do a very quickly screen among of all the samples. Why use chloroform to do that when we can do something much faster that would require less solvent and also less time? So that's where the rapid extraction methods came, which would involve only few grams or milligrams of my fish food sample, extraction, a very quick extraction with only 2 mL of methanol with acetic acid, sonication, and then send the samples for analysis. Note that these extractions is from a qualitative perspective, not a quantification. I also tested 2 different separation methods. I think I may have forgot to mention. So for this part of the project, I use a high resolution mass spec, sorry. And I had 2 different methods for analyzing astaxanthin, one for my RFS column and one for my conventional. Another very important thing to mention as well is for these both methods, I use exactly the same column. The difference is for the conventional, I use a lid and I close the peripheral outlet flow of the column. So then the column would operate as an unconventional column. If you can notice here, the main difference between these two methods is the flow rate. Whereas for the conventional would be 1 mil per minute, for the RFS was 2.5 mil per minute. And here just to bring you a little bit of a perspective of the results. So here I have the extracted iron for astaxanthin. So the peak in 7.2 minutes is when astaxanthin was retained when using the conventional column. And here in 2.8 minutes is when astaxanthin was analyzed using the RFS column, which show us that is actually much faster when we are using this column. I know you must be thinking, okay, Karin, I can say that the intensity of the peak is quite, lower than compared with the conventional. But just don't forget that only 30% of my mobile phase was actually sent to the detector. The other 70% was sent to waste. Another important aspect when we are checking the efficiency of a column is to check the peak width at half maximum. So here I have a little bit of comparison between the peak of the conventional and RFS. And what we can see is even though it's not much difference, but I gained a little bit of resolution as well when using RFS. And again, the intensity of the peaks is different, but it's because of what I just explained to you. Also, I just want to demonstrate how complex a fish food sample is. So here is my total oil chromatogram. We can see that are several peaks here. And for this reason, I did a multivariational analysis called principal component analysis. Is a kind of analysis where we are doing the differentiation of our samples based in the chemical difference that they have. And the reason why I did that is because I analyzed 27 fish foods using this method. And I want to see the difference between them. And when I did the principal components analysis, I red flagged two very important things. The first thing is, important to mention, these 27 fish feeds were choosing because they had in their label that they contained astaxanthin. And what I found out is, one, not all of them has astaxanthin, which is a little bit dodgy. And the second thing is the presence of a synthetic preservative called etoxyquin, which has been banned in so many countries. And when I went to the labels of the fish feeds that contained etoxyquin, they didn't have in a label, which was quite dodgy as well, because this can mislead, customers. So no good. And also, I just want to have a quickly look with you what was the main ingredient approach when using the RFS column. So imagine that we are to analyze about 100 samples. So the first thing is when we are using the RFS column is about time. So while for my conventional method was 25 hours, or most of the published methods that can take 60 hours for analyzing 100 samples, my method only took 10 hours. The amount of solvent when compared to the published method was so much less. I understand that you must be thinking, okay, Karin, I don't see difference in amount of volume of solvent used for your mobile phase, but this is something that I definitely want to be improving as well. And when we are talking about industry, we are also talking about money, and we are also talking about the lab technician that is going to be doing the analysis of these 100 samples. So if we are, to only use 10 hours of their time, is going to probably cost much less for the industry. So just to conclude my presentation today, the main thing for me is I did not lose quality in separation when using the RFS technology. I gained resolution, which was pretty good. And also the analysis was 3 times faster. And the methods do align with the industry protocols for a qualitative perspective or qualitative screening of samples. And important as well, there was so much saving in energy because was so much like less hours used for analyzing the samples. And obviously less solvent when compared to published methods. So a massive thanks to everyone that has been involved in this project. But I will always say a big thank you to Tony and my previous supervisors for giving me the opportunity of being here today. And yeah, that's from me today.